In this slide, we will talk about the round-off errors, which was the topic initially. And up to this point, we actually explained some initial terms to be able to understand this in a better way. And now we can define the round-off error. And the round-off errors, as we said before maybe, originate from the fact that the computers retain or keep only a fixed number of significant figures during a calculation. We said that it can keep, for example, only 5 or 8, or if we write format long, for example, it will keep much more uh, digits, but eventually we will have a truncation of the numbers. That's why we have a round of error. And the numbers like p, exponential, or root square 7 cannot be expressed by a fixed number of significant figures because the numbers in these values are going to the infinity, and we need to cut at some point uh, to keep it short and storable in the computer. That's why they cannot be represented exactly by the computer with the infinite numbers. And also, the computers use a base 2 representation. And in the base 2 representation, they cannot precisely represent certain exact base 10 numbers sometimes. That's why we need to be careful about this and know that we will have round-off errors and discrepancies, which is the differences or round-off error. By the omission of significant figures, we will have a discrepancy or a difference, and it is called round-off error. And the numerical round-off errors are directly related to the manner in which numbers are stored in a computer. So if you are using computers and you have round-off errors because of the omission or cutting at some point, that means numerical round-off error exists. And to be able to define this, first we need to define the base systems, and for those we need to define word. Word is the fundamental unit whereby the information is represented on a computer actually. This is an entity that consists of a string of binary digits or bits. Actually, for example, in computers we have 8 bits, 16 bits, 32 bits, 64 bits. They all have some units, binary digits, or small entity which is called word, and the numbers are stored in these words. Yes, one or more words, they are stored. And to understand how this is done, let's first review some material related to number systems, specifically the base and digits or bits. Let's define them in the following slides. Let's start with the number systems. A number system is only a convention for representing quantities. And as human beings, because we have 10 fingers and 10 toes, the number system that we are most familiar with is the decimal or base 10 system. Because all the numbers we actually speak, write, use in calculations are in base 10 system. And a base is the number used as the reference for constructing this system. So in the base 10 system, for example, we have 10 digits from 0 to 9. By adding these, we will have other numbers as well. So because we have 10 numbers, we will have base 10 system. And by themselves, these digits are satisfactory for counting from 0 to 9. And for larger quantities, we have the combinations, as I said already. And for example, for the 86,409, we can define this as the base 10. So this is actually, let's define this way. 9 is the first digit, which is just in the 10 to the power 0. And we will, let's show this way. We will sum this with, this 0 is indeed 10 to the power 1. 4 is 4 times 10 to the power 2. And plus 6 is 6 times 10 to the power 3. And this is 8 times 10 to the power 4. If we sum these, it will give us 86409, and this kind of demonstration is based on 10 tens, and that's why it's called base 10 system. With this in mind, we can continue on defining, for example, base 2 system as well, which is used in computers. Let's go to the other slides to learn about them. And here you can see an example base 10 system, the example we showed in the previous slide, and we showed these already. With the summation, we will have the number in base 10. We can have the same number in base 2 system. And for that, we will have, instead of tens, 2's. And in the base 2 system, we will have only 2 numbers because it's base 2. In base 10, we had 10 numbers. Here, 2 numbers. And these are again starting from 0. And to be able to have it 2 number only, 0 and 1. So it works with 0 and 1's. And you know that the computers also are working with 0 and 1's. That means they have base 2 systems. And in base 2, you can see we have a similar notation. Powers are from 0 to 7, increasing, and we will multiply them with the numbers that we write. Here we sum them up, and 173, for example. And here we can define another term, positional notation, which is a visual representation of the numbers in base systems. And this is actually positional notation, simply. And we can define the number with this position notation. These are the notations, and simply multiply the number by each position power. Actually, this is 2 to 0 is 1, 2 to 1 is 2, and in the end, sum them all to get the value of the result.